All right, AP Chem, we're back again to learn another concept when it comes to reaction kinetics, and this is the concept of half-life. The half-life of a reaction is defined as the amount of time that it takes for 1/2 of the reactant to be used up. And before we get into the first example of what a first-order reaction's half-life will look like, let's look at the graph at the upper right. Here we start out in this graph, the initial concentration, let's say, is 150. Then if we track the amount of time it takes for us to go, the amount of reactant to go down by half of the initial amount. That amount of time is what is defined as the half-life, however many seconds or minutes or hours, whatever it is. If we then look at how much time it takes for half of that amount of reactant to disappear or to be converted, that is another half-life. That would be called the second half-life of the reaction. And you can have multiple half-lives. In other words, you can start out, let's say, with 150, then down to 75. See how much time it takes to go down to 37.5, how much time it takes to go down to half of 37.5, and so on. But if you kind of think about what is the half-life telling you, if you know the value for the half-life of a reaction, it's going to give you an idea of how rapid that reaction is. If I told you that the half-life of a certain reaction, let's say, and it's designated as T 1/2, like with a subscript 1/2, was, let's say, 12 seconds. And the half-life of a different reaction was 500 seconds. Well, you know that if the first reaction that I mentioned with a half-life of 12 seconds, that's going to be a much faster reaction, because it's only going to take it's only going to take 12 seconds for half of the reactant to be used up, versus the other reaction where it's going to take 500 seconds for half of the reactant to be used up. So the half-life can give you as one number that can give you kind of a quick and dirty read on how rapid this reaction is. Now, just as with the integrated rate law form, each integrated rate law had a separate look to it, different look to it. Each order of reaction has a different half-life look to it. So let's take the first order half-life and kind of look at that one first. In the first order half-life, you could start out with the integrated rate law for that first order reaction. And to determine the amount of time it would take to, use up half of the reactant, in a sense, what you would do is you'd find the integrated rate law, you would have the value for K, you would do the analysis like we talked about in the integrated rate law reaction to find the slope of the slope of the line of natural log of A versus time. That would be the value for K. And then what you would do is you would plug in the initial concentration of A here. Then you would plug in half of the initial concentration, whatever that is, of A here. And then you'd solve for the time that you'd rearrange the equation and solve for the time. And that would be the time for the amount of reactant to go down to half of what it initially was. Now, if you do this with any first order reaction, it actually turns out to be kind of a really cool result. What you would find out is that the half-life of a first order reaction is constant. It is not concentration dependent. It's kind of odd, but this is the way it works. In other words, the half-life of the reaction is going to be 0.693 divided by the value for K. And 0.693, we're going to learn as we go through the examples. Essentially, it's the natural log of 2, because if you do this whole, plugging in initial concentration here and half of the initial concentration here and rearrange and solve for K, it turns out that this ends up being the natural log of 2 over K. And if we look at this graph again at the upper right of the slide, you see that the half-life is about 13,000 maybe seconds, and it's constant. So this is an example of a first-order reaction with first-order kinetics. The graph of concentration versus time is not linear, but the graph of natural log of concentration versus time must have been linear. They found the value for K, and you can see, though, that the half-life is constant. All right, and so all you really, and the neat thing is, all you need to do to know the half-life of a first-order reaction is to find the value of K. And then the half-life is going to be 0.693 divided by K. Looking at a second-order reaction, here's a typical graph of a second-order reaction, concentration versus time. All right. And this, let's say we found that this reaction is second order, and we know it was second order because when we plotted, for this graph here, when we plotted 1 over the concentration of A versus time, that graph was linear. Sorry, that graph is always a positive slope. I don't know why I always do that. And we found the value for K, right? We know this is a second order reaction. To find the half-life, we would plug in half of the initial concentration here, the initial concentration here, and you solve for the time it takes. And what we would find is the half-life for a second order reaction is 1 over K times the initial concentration. It is concentration dependent. So for a second order half-life, though, all you would really, to find each successive half-life, to find the first half-life, you'd plug in K times the initial concentration. Okay, so K times this initial concentration. For the second half-life, you'd plug in 1 over K times the initial concentration. That would be this concentration, like the half. And that would give you the next half-life. To find the third half-life, right, you would plug in this remaining concentration after 2 half-lives. Right, that's what you would plug in down here, because that's really the initial concentration for the third half-life. Then you would find what that half-life is. And you can see that for a second order reaction, each half-life is twice as long. Each succeeding half-life is twice as long. So it looks like the third half-life, however many seconds that is, the fourth half-life would be twice as long as that. Now I can already see that you're saying, all right, already we now have 2 equations. Now remember, we will always get the equations for these half-lives. So it's not like you have to memorize all the integrated rate law forms. You don't have to memorize the half-life equations. That would be given to you on the AP equation sheet. Finally, let's look at the form of the half-life of a zero-order reaction. Again, this would be your zero-order zero-order integrated rate law. Again, to find the half-life, you plug in, the initial concentration divided by 2 here, the initial concentration here, solve for the amount of time that takes. And if you do that, you do the math, this is the equation you would get. The half-life for a zero-order reaction is the initial concentration for the first half-life, it would be this initial concentration here over 2 times K. If you wanted to know what the half-life is for the second half-life, you'd plug in this half amount of concentration in, right? Because it would be the initial concentration for the second half-life. Anyway, you just plug that in, and you'd find that the half-life for a zero-order reaction, again, is the initial concentration over 2 times K. Again, this half-life for a zero-order is concentration dependent, and it turns out that each successive half-life is half as long as the preceding one. So if this one was, looks like it was about 13 seconds, this would be about 6.5 seconds. And then the third half-life would be a little over 3 seconds. Okay, so that's the half-life for a zero-order reaction. Okay, so let's look at an example for first order reaction. Again, this is the equation for the half-life of a first order reaction. Here, it says here, the K for a first order decomposition of N2O5 is this 1.7 times 10 to the negative third per second. What is the half-life? Well, to do this, you'd simply plug in 1.7 times 10 to the negative third per second, right, into this equation, and the answer is 408 seconds. Notice the half-life is in seconds because you're plugging in a number with the units of 1 over seconds into the denominator. So the double denominator is the numerator. So it would be 408 seconds. Now, how long will it take this in the concentration of N2O2 to reach 25%? Well, it takes 408 seconds to get to 50%, right? That's half, all right? So 25% is 2 half-lives. And because for a first order reaction, the half-life is constant, the amount of time it would take to go to 1/4 would be double this, right? Because each half-life is 408 seconds. So this would be 2 half-lives. So you take the 400, because again, first order has a constant half-life. It would be 816 seconds. To go down to 12.5%, that's 1/8, that would be 3 half-lives. It would be 408 seconds times 3. To go down to 6.25%, which would be 4 half-lives, it would be that 408 seconds times 4. Okay, again, first order kinetics, the half-life is constant. Now, before we go on to this example, let me just tell you that the first order half-life problems are way more prevalent. And in fact, the College Board on the AP exam will concentrate for their half-life questions on first order half-lives. And so before we go through this example, if you do look at your AP equations and constants sheet, you do see that the only half-life equation that appears on the AP equation sheet is that 0.0693 over K, which is first order half-life equation. Now, I'm going to expect you to be able to handle second order and 0 order half-life problems, but again, you will be given those equations. Okay, so let's look at this example. It turns out that the radioactive decay of radioactive elements always follows first order kinetics. It's not a chemical reaction, it's a nuclear reaction, but the amount of time that it takes for half of a certain amount of a radioactive substance to decay radioactively into another form, another substance, is follows first order kinetics. And that would mean that it has a constant half-life. Now, except that in the case of radioactive decay, the value for K, this rate at which these radioactive compounds break down, their nuclei break down, is not called the rate constant, it's called the decay constant. Again, it's not a chemical reaction, it's a nuclear reaction, and the rate and the nucleus of the radioactive element is decaying into a different element. So let's look at this question. The decay constant for the decay of sodium-24, that is the isotope, radioactive isotope of sodium that has a mass number of 24, is 4.63 times 10 to the negative second per hour. What would the half-life be? Well, T1/2 is simply going to think of this decay constant as K. It's going to be 0.0693 over K. And of course, it kind of got covered up by my writing. There, I corrected it. So the way this would be that T1/2 would be 0.693 over 4.63 times 10 to the negative second per hour. Again, that number would then be 15.0, and then hours would come up into the numerator. So it would take 15 hours for half of sodium-24 to decay. All right, let's look at the next one. The half-life of radon-222. So if I have a lump of radon-222, right? All right, and it's already at radon-222 in this amount. After 3.28 days, half of this has decayed into some other element, and I believe this would decay into a form of radium, not radon, if I remember correctly. So anyway, then you would have half of it. All right, so every 3.28 days, half, so this would be gone after 3.28 days, then half of the remaining amount after 3.28 days, and then half of that remaining amount after another 3.2 days, and so on. So what would be the K value for this? So what you would do is you'd say that T1/2 is 0.693 over 3.28 days, right? And then you would solve, I'm sorry, I'm wrong. The T1/2 is 3.28 days, and that's 0.693 over K. So you would solve for K. So sorry about that mistake, but here we go. Let's see what the answer is. It would be just simply rearranging that equation and solving for K. So the rate constant, or the decay constant in this case, would be 0.211 per day. Okay? And again, last, let's kind of look at the summary slide. Now, we saw the summary slide before when we were talking about integrated rate laws. We saw that we went over this. Let's look at this last line. And again, these would be equations that would be given to you. For first order, constant half-life, it is not concentration dependent. Again, this equation will be on the AP equation and constant sheet, as will this one, and this one. But how about a zero order? Zero order is concentration dependent, and the half-life would follow that equation. Second order is also concentration dependent, and the half order would follow that equation. So that's pretty much it for half-life. Again, just to get used to this, you would have to do some practice problems, and as usual, there will be a worksheet that follows these notes. All right, signing off again. Take care.